In this video, we're going to learn about equilibrium expressions and Keq. So as a refresher, at equilibrium, the concentrations of products and reactants are constant. Although the forward and reverse reaction are still occurring, they're occurring at equal rates, and so the concentrations of products and reactants will not change. If we look here, we have for a reaction between substance A and B that forms substances C and D. The equilibrium constant can be calculated according to this. I just want to kind of flesh this out a little bit. We have, note, the product side will be in the numerator and the reactant side will be in the denominator. And note that we're taking the concentrations of everything. So the concentration of one product raised to the power of the coefficient from the chemical equation. We'll multiply that by the concentration of another product raised to the power of whatever the coefficient is from the equation. And then we'll divide that by the same thing on the reactant side. I know this is a little bit difficult to visualize without actual substances, so we can take a look at an example. Let's consider the system of NO2 at equilibrium with N2O4. On the left side, we've got the N2O4, and on the right side, we have NO2. And so the K, the equilibrium constant, is calculated as it is at equilibrium, the concentration of NO2, the product side, squared, it's squared because of this coefficient of 2, divided by the concentration of N2O4. So at equilibrium, whatever the concentration of NO2 is squared divided by the concentration of N2O4, that quotient will be the equilibrium constant. And it's notable that you're going to get that pretty much no matter where you start. So for example, if we start with a system initially where there is absolutely no NO2 and 0.670 molar N2O4, well, in that case, the N2O4 will break apart to an extent to form NO2. And that system will reach equilibrium when the concentration of NO2 is 0.0547 molar, and the concentration of N2O4 rather is 0.643 molar. Now, if you were to take this value here, the 0.0547, and square it, and then divide that by 0.643, you would get the equilibrium constant, which is this. Now, if you started with a different system where there was a little bit of NO2 to begin with, and this amount of N2O4, notice you've got less N2O4 to start with, and you've gone from 0 NO2 to some of it. Well, even so, the equilibrium would still be established where the quotient of concentration of NO2 squared divided by the concentration of N2O4, those values being here, that will come out to the same thing that we had in the previous scenario. And if we start with even different concentrations, we'll still end up with concentrations such that you do this math and you'll get the same equilibrium constant. Now, if you're paying close attention, I know you'll notice that the hundredths column or the hundredths digit is going to be a little bit different among all of these. Chalk it up to experimental error. These are essentially statistically identical values. A couple other things. It's worth noting that equilibrium constant is something that can be expressed not only in terms of concentrations, but also in terms of partial pressures. So sometimes you'll have concentration of aqueous solutions. Sometimes you'll have concentrations of gases. Well, you can also have partial pressures of gases. And note that in the previous slide, the equilibrium constant, that K value, was equal to the concentration of products over the concentration of reactants. In this case, it's the partial pressure in both cases. So I look here, I put products, the N2O4, I put the partial pressure of the product N2O4 in the numerator and the partial pressure of NO2 in the denominator. Note, of course, that I'm squaring this because of the coefficient of 2. Moving on, another very important detail is that solids and liquids should always be left out of equilibrium expressions. So if I'm writing out the equilibrium expression for this process, I'm going to say that K is equal to, I look to the product side, and I see that the calcium ions are aqueous. So I'll say the concentration of calcium ions, and I'll multiply that by the concentration of the chloride ions. And of course, because the 2 is here, I'm going to square that. And I divide by the reactants, except wait a minute, my reactant is a solid, it's not aqueous or gas. Again, solids and liquids are to be omitted. Aqueous and gas are the only phases that should be included in the equilibrium expression. So the equilibrium constant is calculated according to whatever the concentration of calcium ions times the square of the concentration of chloride ions at equilibrium. And one final note, the magnitude of K. What does K even mean? Well, if K is very, very big, if it's much bigger than 1, that means the reaction essentially goes to completion. And an example of this is if we have hydrogen and we have oxygen and we mix them together at 500 degrees Celsius, the equilibrium constant is enormous, on the order of 10 to the 47th power. That is because K is equal to the concentration of H2O, and I realize this is not balanced, it should be 2H2O. So the concentration of H2O, and I'm going to square that, and I'm going to divide this by the concentration of the reactants. So I've got H2, and because it's 2H2 in the equation, I'm going to square it, times the concentration of O2, which is only to the first power because there's only one O2 as the coefficient here. So if I look at this quotient, and I know that this is equal to 2.4 times 10 to the 47th power, well, that means, if this is to the 47th power, that means I've got a lot of product and not very much reactant at equilibrium. So this means that the reaction very much favors the product side. And if it's so much greater than 1, truly, if it's anything greater than 1,000, the reaction has basically gone to completion. It's basically gone to 100% products. By contrast, if we have a very, very small equilibrium constant, like here, on the order of 10 to the negative 55th power, then the reaction barely goes forward at all. In this case, we're dissolving Pb3, well, it's lead 4-phosphate, I'll say that. So this dissolution of lead 4-phosphate, that equilibrium constant is going to be equal to the concentrations of the products. We've got Pb positive 4 concentration to the third power because of the coefficient of 3, and I'm multiplying it by the concentration of phosphate ions raised to the fourth power because of the 4, and I'm going to divide it by nothing because this starting material on the reactant side, this is a solid, so it's out of the equilibrium expression. But what I can say is that if I take this stuff, this is a powder, and I try to dissolve it in water, what I will find is that that will reach an equilibrium where the concentration of the lead ions cubed times the concentration of the phosphate ions to the fourth power is equal to something unbelievably small, 10 to the negative 55th power, almost 10 to the negative 56th power. So what I can say is that in this case, this side is very much favored. And since the equilibrium constant is so low for this, reaction, we can say that lead 4-phosphate is very, very insoluble. Because again, at equilibrium, the concentrations of the aqueous ions are extremely low. By contrast, up here, Water is a very favorable substance. You're not going to get much water decomposing to H2 and O2. And that's indicated by the magnitude of this huge, huge equilibrium constant. So that's all on K. And if you have any questions or comments in the comments section below is where you should leave them. So hope you've enjoyed this video. All the best.